opportunity to be here today. First, how's my volume? I'm rarely too quiet, and I think that's okay now as well. Good. I can't help but think the last speaker was talking about me when he was referring to the presentation with the longest title. I may have taken that one away. But again, my name is Jonathan Brandenburg, and I'm with a engineering company out of Houston, Texas called METECS. And I'm going to start with telling what my motivation is. Like, why am I talking about a hardware-in-the-loop test environment for, small satellite GNC environments? And the short answer is it's a nice intersection of some of the skills. So we've started developing some hardware and software algorithms for CubeSat, attitude control, astrodynamics, and that kind of control. And the real question we have to ask ourselves is, how do we know it works, right? And we've all faced the testing and verification and validation problems. So how do we know that our attitude control algorithms are going to work? And so to that end, we went down that path that I'm sure some of you have as well, of developing a ground-based test environment. And I'm skipping a lot of slides that I really hope you'll go back and look at, saying what a wonderful organization we are and what our skills are. But I want to focus on the technology today. And so we went down the path of developing our own Helmholtz cage. And I imagine many of us are familiar with that. It's a sphere or a cube capable of producing a desired magnetic field. We often use it to reproduce the magnetic field that a satellite might experience in orbit. And so we started down the path of designing one of these and building one of these. And the reason we did that was because we were building magnetorquers and integrating magnetometers into our satellite bus. And we're really interested in testing those in a ground-based environment. And so I set my interns last summer out to developing a Helmholtz cage, and they did a fantastic job. The first thing they did was build this little tabletop model. It's about this big. And as much as I really would like to take this home and display it, my wife tells me it does not go in our living room, so it's going to remain at work for now. But what we proved very, very quickly was that this concept was very viable. We were going to be very capable of building a ground-based magnetic test environment. And so what I'm here to do now, the rest of the presentation, is talk about some of the lessons learned. Again, kind of like we heard from our previous speaker, right? What went well and what didn't well? What did we learn? And one of the things I learned is you have to pay attention to detail. And I know that picture is fairly small, but if you look really closely, you may see something that I myself overlooked when my interns built this. It turns out that when this was built into a full-size frame, we went to a full room size, approximately 8 feet tall. It kind of collapsed. If you look at the corner brackets on those, you realize they were not triangular in their forces. They were rotational in their forces. So once we hit a certain size, we had a mechanical challenge with that. But after picking that back up, we really came into some of the core challenges that that anybody would run into when developing a magnetic ground-based test environment. You already mentioned the second one, the structural stability. But the first one was how do you run the right current through this? One of the interesting aspects, of course, of magnetic fields is they can reverse. And if you reverse a field quickly enough going through a coil, you're going to have a lot of collapsed field, a lot of collapse-induced current. And we wanted to avoid that very badly, as you might imagine. So we went through several iterations of power supplies. In the end, we ended up finding that audio-style technology worked really, really well for driving these coils. So that's one of the first lessons to take away when we were in the process of building this ground test environment, is that the power supply turned out to be the hard part, not the part that I was worried about, the physical assembly, but instead the powering of it. So we did really, really well on that. The other problem we ran into was field measurement. And this is where I learned that laboratory magnetometers have two different technologies they use to measure the ambient field. And one of them, if you, logically speaking, and this is a little outside my realm of expertise, but if I'm measuring the field this way and I turn around to measure it this way, I would expect those to be opposite in value, but similar in magnitude of sign. But unfortunately, some of the magnetometers, the laboratory magnetometers you have, don't measure that way. They're very sensitive to the ambient field. And it took us probably a good few months to really understand that and drive that to ground. Since then, we've acquired another magnetometer for our testing, and I'm much happier with the results of that. But the end result of this was actually very, very successful. We have an 8-foot machine in our bay. It looks a lot like a time machine, and in fact, there's a sign on it that tells you to make sure you be careful before entering the field that you enter the correct time and date. But it actually has created a very stable field, approximately 1 cubic meter. And we ran the math on that to see how much space we would need to stabilize a field. And it turns out this approximately 8-foot tall Helmholtz cage gave us that desired 1 cubic meter of stable space inside the field. We were also very gratified to see that it has an extremely linear response. And we were even more gratified to figure out that we were within 1% of the theoretical targets. We're driving this from a MATLAB simulation, controlling those audio amplifiers through a lab jack, and the field was able to precisely model the field a satellite would experience in orbit. And I guess I should probably recognize the obvious, that this only is useful if your satellite's going to be within an Earth's magnetic field or some other magnetic field. Some of our deep space satellites, for example, wouldn't benefit from that. But if we're looking at LEO or MEO or even highly elliptical, there's going to be a lot of benefits to this type of technology. So that's one of the things that I consider a success. But then I had a second problem to solve, which was once I had my test article in hand and I have my Helmholtz cage here, how do I put the test article in the Helmholtz cage? And I will admit, my first thought was hang it from a string. Right. And I'm pretty sure many of us in this room may have already done that as well in your experimentation early on. But I did very seriously consider hanging it from a string and just letting it rotate freely. But I ended up finding a very cool technology called an air bearing. I'm sure you may have seen those. You know, you've also seen those old air hockey tables back in your day, where it runs compressed air through this device and it floats that center bearing on a very, very fine layer of air. And this is a very precision and very interesting instrument in the sense that it's made from sintered fiber, carbon fiber. So it's almost just a pure air field all the way around it. And what we found is once you run the appropriate pressure of compressed air through this, it has effectively zero friction in practice. This is one of those things that we were able to buy and plug in the field, and boom, it worked. We were able to put a test device on there and it spins very, very nicely. So those, again, I'm going to celebrate. But the other aspect of what we were doing was not just involving magnetorquers and magnetic field operation. We're also interested in, of course, modeling another common attitude device, the reaction wheel. And so we were purchasing some commercial reaction wheels. We're building some in-house. And then the question really comes down to how do you test reaction wheels very effectively? And to do that, we ended up building what is often termed a rate table. In this case, we have basically a geared system at the bottom with a motor sticking in the side, and the motor spins and it rotates the rate table around according to whatever current you're feeding into that motor. And you ask how that might help. Well, what we ended up doing is we ended up basically building a closed loop control system on this. We put an extremely sensitive force sensor at the base of that rate table. And with our test article on top of it, if the reaction wheels in there torque that test article just the slightest bit, we feel it through the force sensor. And then we're able to feed that back through the control loop on the MATLAB controller and then adjust the rate table speed. And this actually still shocks me when I see it work because it's just almost magical when you breathe on that fork that you see in that image and it starts spinning and keeps spinning. Or you put your finger on it and it stops and reverses. That's actually really, really interesting and really cool. We did run into some issues on that, though, primarily the fact that if you're not perfectly balanced, as you might imagine, that force sensor is going to constantly be detecting some sort of sideways force. And we ended up having a technique whereby we pre-measured that force and we're able to subtract it out of the closed loop simulation calculations to do that. We also have problem with flex and rebound. There's a natural, action-reaction kind of problem once a motor starts turning, and there's also some gear, not slack, but a similar term, it's escaping me. All those you have to deal with as well. But ultimately, we got it working. We ended up initially testing it with a gyroscope, just a battery-powered gyroscope we'd spin up and watch it turn in reaction to that. If you look on Amazon, you'll find a super precision gyroscope, which looks like this very impressive aluminum gyroscope. We ended up using that in here, and it's got really good bearings. But what we found is that our sensor was so sensitive that it would actually detect the friction in those bearings as being a rotational force. So that actually turned out to be a nice positive validation that we were able to detect very, very small forces inside our reaction wheels. So what we've effectively done here is figure it out, not earth-shattering, I know, but certainly a capability and some lessons learned here that perhaps you'll benefit from. An opportunity to build the magnetorquer and reaction wheel control system, and then a ground-based test environment to test that in. And I've got some pictures here talking about the magnetorquers, and some of these we built in-house, some of these we've outsourced, and some of these we've purchased commercially, just to make sure we completely understand the various pros and cons of this particular technology. And I'm real happy with that. And with that, I kept it short, and I think I may have time for questions or complaints if you're interested, please.